Hello. So my name is Katherine Driggs-Campbell, and I'm an assistant professor over in the ECE department at UIUC. So today we're going to be talking about ways we can start thinking about how we can design human-robot systems that are both safe and interactive. Now, I know I'm in the session on explainability and predictability, and we won't be talking about that explicitly in this. We will be talking about prediction, but not explicitly some of this explainability stuff. But instead, we're going to start thinking about or making the claim that if we can start thinking about how we can encode or represent interactions between different humans or between humans and robots, we can come up with better robot policies and enable better robot learning. So we're going to focus on, again, representing and encoding these sorts of interactions for learning robot navigation policies. And again, hopefully, what we'll show through our results is that by doing this, at the end of the day, we do get policies and robot behaviors that are more understandable and that typically perform better in shared spaces with people. So I'll be talking about some of our work in how we can represent some interactions for robot navigation. And then we'll be doing a deep dive into another way we can represent interactions specifically for prediction. And that will be presented by one of my senior PhD students, Zhe Huang. Okay, so as a little bit of a motivation, let's think a little bit about why we care about this sort of interaction and whatnot. So at the end of the day, we want humans and robots to share the same space, and we want them to do it in a safe and efficient way. So here's just a quick motivating example of some of the challenges or some things that we might want to hit home. So here we're going to have a very simple system where we have this robot arm that's right here, and it is sharing a space with a human who's going to come into the picture in a moment. We have a sort of a simple safety system to start, where now every time the human enters the robot space, it just stops here. So this is a purely safe system, right? It's optimized, so anytime the robot and human are sharing a space, nothing's happening. So here we have very high safety margins. There's very little chance of something going wrong. However, very low on the interaction front. We're basically getting no interaction, no collaboration going on between the two. And we also have very low efficiency here. And this efficiency part is really exacerbated when you start basically having this human moving at higher speeds, or basically the robot is kind of in this landlock. It's basically stuck in space and is really unable to do anything. So by not considering the human a little bit more carefully, yes, we have good safety margins and good safety sort of performance, but we are really lacking in terms of the efficiency and interaction. This is also true in many other cases. You can look at this in the autonomous driving case, where you can hold up traffic if you're not properly understanding what's going on around you. And at the end of the day, you can actually cause more harm than good and start to compromise safety by not more considering the human more carefully. So this is just some simple examples of when we have these humans and robots sharing some spaces, we really need to think about how we can start balancing ways we can improve or increase interaction while still providing safety and getting the job done. So today we're going to look at two different ways we can start modeling and understanding the human. We're going to do this by basically trying to understand and predict interactions between people. And we're going to rely a lot on graphical representations for this. So the first one, we're going to think about ways we can capture or represent influences between different agents to find better robot policies. And then the second thing we're going to do is look at some prediction methods for human motion. So hopefully we can then inform planning and at the end of the day, again, safety. So let's just dive right in. And one of the main motivations we're going to look at is the challenge of robot crowd navigation. So in robot crowd navigation, we have a robot that is sharing a space or maneuvering around a bunch of human agents, as shown here. Nowadays, it's very popular to take a reinforcement learning approach to this. Since we're working in this very high dimensional state space, we have these sort of hard to model human agents. So there's lots of things that are great about the reinforcement learning paradigm for learning effective robot policies in the space. So here we have the observations of these different humans. We have the robot state policies, and we want to take these, or the robot states, we want to take all of these observations and map this to actions to help us get to some goal. Again, what we're going to try and do is really think about how we can understand what's going on between the different agents, see if we can try and incorporate some predictive or some sort of forethought into what the humans will do to get that sort of deeper understanding, similar to what humans naturally do, to see if we can get better policies at the end of the day. Okay, so we're looking in this space, and one of the things that I think is interesting about crowd navigation is you think about problems with humans and robots, and they really are just compounded since we have lots of humans operating around. And there are some sort of really interesting challenges that arise because of the intricacies of dealing with or interacting around people. So one of the challenges for this is really dealing with some limitations of the robot. For example, we might have a limited field of view. So here's some model-based approaches that we could look at here. Let me pause this for a moment and replay this. So if we have limited sensor field of view for our robot here, so a robot is this yellow agent. This cone represents the field of view. These other circles are human agents. This star is our goal. So we have these this robot that is navigating through these in this human space and trying to reach its goal here. So in the case where we have a limited field of view, and there's many agents that will come in and out, and we often really have a hard time as coming up with this. So this is some model-based approaches, which we'll see have a struggle a great deal with this, since they typically have to detect the humans and then determine what they're going to do. And then over here, we have some state-of-the-art RL approaches, which will be our baselines for comparison, which typically can handle some of these issues with field of view. Since by taking a reinforcement learning approach, we're not assuming a model about what's going on, and we're able to basically implicitly learn what these agents are going to do. So for the most part, we can handle some of these limitations, although we still struggle a little bit in terms of timing. Another thing that's really challenging is when we have dense crowds or lots of agents that are happening at once. If you take a model-based approach, you tend to have this problem where the robot tends to just sort of freeze up because it's basically considering all of the possibilities and can't find a good solution. Depending on your approach for RL, though, this will often actually have the same issues where we are not really thinking about the interactions. This sort of implicit understanding no longer is valid and no longer solves some of these problems. So we have sort of two key challenges that we've identified. One, dealing with limited sensor views, which again is basically thinking about how we can understand the comings and goings of people. And two, dealing with dense crowds, which is really, again, when you have high numbers of human agents all interacting, can you handle this in an efficient way and result in good policies? So one of the things we wanted to argue was that by explicitly capturing influences between agents to model these interactions, we can alleviate many of these problems in navigation. So this is our approach we call the decentralized structural RNN approach, where we can effectively handle both the limited field of view case and the dense crowds problems by, again, taking some of this knowledge and structure that we as people know and trying to code this into our robot policy. So we're going to model these interactions using an ST graph and building off of the structural RNN, which is a well-known approach to handling ST graphs. So we model this scenario with nodes that both capture the robot agent and all the other human agents, and we connect them spatially, which basically capture the relationship between the different agents that we can detect, and temporally. So this is basically how these evolve over time here. So we can decompose this ST graph into a factor graph. We basically are then able to factorize this robot policy into a function of these smaller factors. So basically what this is allowing us to do is it allows us to basically split up this complicated problem, or instead of just taking raw observations, we can break this up into these smaller factors. So we can break these up into separate things that we need to learn. So we can basically focus on learning a specific thing a little bit more efficiency. So we can incorporate this into our robot policy here. Another thing that we do that's a little bit different from the traditional structural RNN approach is that, as I mentioned, we take what we call a decentralized approach, but because we know a little bit about the interactions that happen and what we care about, we can actually parse down the edges in this graph a priori. So for example, we know we don't care about the spatial edges between the other people, since this is sort of already understood within our own edges and in our own observation space. So we can parse this down a little bit. So we can take take a more decentralized view to the problem here. So here's our network architecture. Again, basically what we're doing is we're taking this factor graph approach so we can learn the different factors independently, or not independently, but in particular. So first we are able to learn the spatial interactions between the humans and the robots. We're able to learn the dynamics of how the robot interacts with the different agents, and then we combine this all together. So then we can combine this all to basically determine what the best action is in this sort of traditional model-free reinforcement learning take on things. So this really simplifies the overall pipeline and allows us to sort of avoid converging to suboptimal policies too early, and ultimately has good performance in the crowd navigation task. So here's some baseline performances against the model-based approach and one of the state-of-the-art RL-based approaches. You can see in both the varying field of view case and in this increasing number of humans, we're able to get really good performance in simulation. We can also transfer this to the real world, where here we have the robot view, and here is a small but a crowd that the robot is going to navigate through. So here you can see with this robot view, it has a very limited field of view here, but it's detecting and remembering some things about the humans, encoding the interactions that it sees, and then effectively operating through here. So again, by basically enforcing some structure and representing that interaction in the robot policy, we're able to get better performance and outperform state-of-the-art currently. So this is just one way that you can think about trying to encoding or representing interactions. Another common approach that people typically do, though, is by detecting the humans around them and then performing some sort of prediction on top of that. So if you have a good prediction of what these human agents are going to do, then you can make effective decisions yourself as a robot that can maybe think a little bit longer, have a little bit of a longer time horizon to think about there. So now I'm going to pass the time over to, again, my student, Zhe Huang, who's going to present his work on a new prediction method. And one of the things that I would like to highlight about what he's going to talk about is that this approach specifically addresses some of the biases and some of the issues inherent in some of the current data sets that are often used for predictions. And he really looks at how we can algorithmically address them. So I will pass the time over to him now.
Hi everyone, I'm Zhe Huang from Human-Centered Autonomy, University of Illinois at Urbana-Champaign. I'll present our work on learning sparse interaction graphs of partially detected pedestrians for trajectory prediction. To enter our daily lives, an autonomous mobile robot must comprehensively understand dynamic human environment. Specifically, pedestrian trajectory prediction is important for mobile robots to safely navigate through human crowds. We are focused on the problem that given trajectories of pedestrians in an observation period, predict their trajectories in a following prediction period. Here is a video clip of pedestrian motion in the crowd. We can see that pedestrians come in and out of the scene frequently. Given a defined observation and prediction period, there are usually pedestrians who do not show up at all time steps. We also see that a pedestrian does not have to observe every pedestrian in the scene in order to safely navigate through the crowd. The pedestrian rarely looks at neighbors at his or her back. A pedestrian usually does not pay attention to every neighbor in the front, but only the important ones. Previous works usually hold two assumptions, which do not align with our observations. The first assumption is fully detected pedestrians. Each pedestrian's position is measured at each time step of both observation and prediction period. The second assumption is full connection. The pedestrian pays attention to all pedestrians in the scene. To understand the first assumption, we can look at an example here, where we plot trajectories of pedestrians in a defined observation and prediction period. The pedestrians with orange trajectories are not fully detected, because they either join the scene later or leave the scene earlier. Here we circle them for clarity. The first assumption essentially forces the algorithm to ignore these pedestrians and only models the other fully detected pedestrians. The incomplete pedestrian data can cause bias modeling in social interaction. We found this fully detected pedestrian assumption results in 41% pedestrians are ignored in benchmark datasets. The second assumption about full connection can lead to excessive influence of unimportant neighbors on the target, especially when the scene has a high crowd density, and it can lead to overly conservative behavior. To handle these assumptions, our work takes partially detected pedestrian trajectories as input. We consider pedestrians who appeared at some time steps during the interested period. Second, we impose sparse connection, such that the target agent pays attention to n most important partially detected pedestrians at each time step, where n is a hyperparameter. To better explain our method, let's consider this demo set, where we define a 4-step observation period and there are 4 pedestrians represented by different geometry shapes. Among these pedestrians, triangle and square are partially detected pedestrians. Our method models all of the pedestrians. At the beginning, we build an interaction graph for each time step. At t-3, there are circle and pentagon, so we create a fully connected interaction graph including both of them. Note the graph includes self-looped edge. At t-2, the square joined the scene, so we add the square to the interaction graph. At t-1 and t, all 4 pedestrians appear, so the fully connected interaction graphs at t-1 and t include all 4 nodes. We want to model sparse connection instead of full connection. How to infer a sparse interaction graph from a fully connected interaction graph? We take the t-2 case as an example. We first build a graph with the nodes same as the fully connected interaction graph, but there are no edges. Next, we select a pedestrian as a target, for example, the circle. We create a feature vector for this target and each neighbor node, including itself. A feature vector is composed of the target node feature, the neighbor node feature, and the feature of edge from the target to the neighbor. We feed all feature vectors into the self-attention mechanism to model relationship between target-neighbor interactions. The intermediate feature outputs from the self-attention mechanism are directly fed into a multi-layer perceptron to generate a probability distribution over each target-neighbor interaction. We apply Gumbels of max to sample the most important interaction from the probability distribution, and then we can add an edge from the target to the corresponding neighbor node. Note that we use Gumbels of max because we want to make the sampling process differentiable. We can use n-hedge self-attention so that n edges will be generated for one target. In this demo, we set n as 2. We will do the same step with each other node as target. It is possible to sample the same interaction from multiple heads. We treat this case as generating the corresponding edge once. We do the same edge generation step for the last node. And then we add the generated edges together and we get a sparse interaction graph at t-2. We name this edge generation module as edge Gumbel selector, and these steps are parallelized. In the example, we did the sparse interaction graph inference at t-2. We can run the edge Gumbel selector for each time step in parallel, so that we can get a sequence of sparse interaction graphs. Given the sparse interaction graphs, we can perform spatial encoding for pedestrians at each time step. We use the adjacency matrix to represent edge existence in the sparse interaction graphs. And we adapt social transformer to take the adjacency matrix as the attention mask for spatial encoding. We name the spatial encoding module as node transformer encoder. The previous steps are all performed independently at each time step. So after spatial encoding, we need to encode pedestrian features temporally. To handle partially detected pedestrians, we adapted LSTM to process features no matter whether pedestrians are present or not. We call the adapted LSTM as masked LSTM. The fully processed pedestrians features at the last observed time step are fed to a multi-layer perceptron to predict the positions at the next time step. We can use the predicted positions at t+1 and perform the whole process again to recursively predict the future trajectories. We named the whole framework as Gumbel Social Transformer as GST, and here is a review of the architecture. We evaluate our work on each scene of ETH-UCY benchmarks independently. Our work reaches state-of-the-art performance compared to baselines in terms of all metrics. We perform a comparative study over various configurations of GST. In addition to ETH-UCY, we include 4 scenes from TrashNet++ challenge. We found GST performance is affected by crowd density of the scene. We also observed that using partially detected pedestrians as input generally has a bad performance than fully detected pedestrians. Here are some qualitative results. We can see the sparse interaction graphs evolve through time as target will pay attention to different neighbors as people are moving. We further evaluate GST model in multi-agent simulation. We run the trajectory prediction models trained with different configurations in multiple human-robot interaction scenarios. We visualize the motion of human and robot agents. We also showed connections with robot as the agent, as the target, and the learned attention weights based on the interaction graph. We can see in the sparse setting, the robot can navigate through crowd, while in the full connection setting, the robot is affected by all neighbors and makes an unnatural U-turn. In this scenario, we can see that by considering partially detected agents, both the robot and the right pedestrian avoid running into the other pedestrian who appear later in the scene. In the last scene, we can see that by imposing a sparser configuration with a smaller n, the robot motion will not be affected by unimportant randomly moving neighbors. Here are the conclusions. There exist 2 common assumptions of existing trajectory prediction methods: full detection and full connection. Full detection ignores pedestrians who do not appear at each time step in the considered period. And the full connection requires target pays attention to all neighbors in the detected range. We adapted the architecture to be able to encode features of partially detected pedestrians, and we train sparse interaction graph inference in an unsupervised way. Considerations of partially detected pedestrians ensures a complete view of the scene. And sparse interaction alleviates the freezing robot problem and minimizes influence from unimportant neighbors. And appropriate sparse configuration is dependent on scene properties. A fixed configuration constrains the generalization across scenes with different crowd density. Though our method performs well in the independent setting of the benchmark, it does not have a good performance in the lib1L setting, which means training with other scenes and evaluating on the one left. Extension of the method with learnable sparsity would be a promising future direction. Here are the references. I'm happy to take any questions.
All right. Well, hopefully we'll get some questions with Zhe at the end of this or after the fact, I suppose. So just to sort of recap or sort of contextualize a lot of what Ted was just talking about, one of the things we really want to do is start thinking about how we can take these prediction methods and start encoding them or incorporating them into our robot navigation stacks. So one of my favorite things about a lot of Zhe's work is that it has been integrated into a lot of different systems. So into pedestrian prediction to help inform autonomous vehicle decision-making, but also has been slightly modified so we can do things like predict human arm motion and have more collaborative robots. But to bring it back to our example on the crowd navigation. So we are able to effectively, basically with a slight modification to how we are formulating our network architecture, incorporate these predictions from the GST approach into the robot prediction. So again, here we have the yellow robot, the detected pedestrians, the prediction for them, and is trying to reach the goal. So it is, if my video will continue to play, I will click through it. Yeah. So it's able to basically effectively predict and help improve navigation. So we have, again, hopefully more human-like behaviors here. This can also be incorporated onto the real system again, where we're detecting, predicting, and tracking these human agents here. Okay, today we talked about how we can represent and encode interaction in two different ways. One is through this graphical approach, through using a structural RNN and an ST graph, and incorporating this into our policy. And the second is by having better prediction, which again, then we can incorporate into our robot planning. And again, one of the things that we've shown is that from this, we can get better performance in our robot crowd navigation application. But the hope is that because we are getting better performance, we're also sort of as a consequence, getting these robot policies that are safer to deploy in these human spaces and also have sort of this increased user acceptance. But as a quick dirty laundry slide, so I'll give a few different things to think about for these different things that we've chatted about. So for the prediction approach and the method that Zhe talked about, one thing is that when we're thinking about this interaction graph, it's really dependent, or the performance of the prediction is very dependent on the sparsity parameter. And that's one of sort of the key insights, but it's very dependent on the scene, and it's very hard to sort of pick or select a priori. And this is one of the extensions that Zhe is really interested in thinking about. But this is something that makes the sort of the insights a little bit challenging. In the crowd navigation work, most of the highlighted results and a lot of the sort of cool statistically significant stuff is all done in simulation. And this is something that is hard when you're thinking about humans and robots interacting, since you're not really working with humans. And while we are able to deploy it on a robot, getting things reproduced effectively in a crowd is very challenging. This is also quite challenging in the time of COVID. So hopefully there'll be more crowds around. The other thing is, what I've been sort of reiterating is that I'm claiming that by encoding and representing interaction, we can improve things like predictability and user acceptance. And this is intuitive, since it seems like we're capturing some of the structure and some of this human intuition. However, really showing this is very hard, especially in the mobile robot case. The mobile robot case is particularly challenging since you don't have repeated interactions often. It tends to be sort of one-off, very short-term interactions here. So it's a little bit tricky there. And the performance tends to be very sensitive to the human reaction, which is hard to account for in all cases. So those are some of the issues. I'm looking forward to chatting with you about what you think of our work, as well as some of these, what we've swept under the rug here. I'd like to acknowledge all of my students here. In particular, I'd like to thank Shuijing Liu, who led most of the crowd navigation work. And thanks to all my sponsors. And thank you for listening. So I'll happily take questions at some point. So thank you.